So second chapter, elements, compounds, and mixtures. They've given a few examples of the common daily life uses of some specific elements or compounds, or even mixtures. For example, you can see a gold ring. A gold ring is usually made up of 18 karat gold, which means a little amount of huge amount of gold, but a little amount of some other thing in the mixture, usually copper. Pure water is a compound, but we do not drink pure water, something you've probably already familiar from previous classes of science, that we actually drink mineral water. By mineral water, we mean some salts are dissolved into water, which means that's also a mixture. So yeah, we do understand the purity of compounds is important, but that doesn't exactly mean we keep using the pure compounds all the time. A lot of our daily life examples are elements, some of them are compounds, and some of them are mixtures as well. So let's get started with the first and most basic of definitions, elements. Now, elements are the substances that can be split into anything simpler by chemical means, which means they have a proper identity. And what we do is that we collect all those identities, and we have even constituted a table that is actually a collection of all of those identities, and we call it a periodic table. We cannot split them into anything simpler, which means one element will only consist one type of atoms, right? So, for example,
Yes.
if there is a metal, pure metal, such as magnesium, it would only consist magnesium atoms. If there is oxygen gas, it would only consist of oxygen atoms. If there is diamond, which is actually a form of carbon, it would only consist of carbon atoms. So in these models or diagrams, what we are trying to show is that different atoms may arrange differently. You would see that this arrangement is entirely different from this one or from this one. We're also trying to show you atoms of single color or size to give you an idea how they look like, or how they might attach with one another. But there is one very important point. Isn't it? It isn't completely true to say elements consist of only one type of atoms, right? A better way of saying that would be all the atoms in the elements have the same atomic number. Why not one type? Because of the term isotopes. Are you familiar with the term?
Yes.
Okay, we're going to clear the term in chapter 3. Sometimes the reason for not doing this chapter in the proper order, instead you might have seen that teachers usually start with chapter 1, then they follow on to chapter 3, and then they come back to chapter 2, is because the concept of isotopes is explained in chapter 3 first. So it's easier to understand this specific point and every related point to this one in the same chapter, right? So if you know about isotopes, you'd understand that not all the atoms of the same element are same. They may have different mass numbers, or they may have different number of neutrons. Both mean the same thing. Now, if you're clear, let's move on to the next page. Are you?
Yes. Yes.
Good. So moving on, that collection has 118 elements. We call it a periodic table. Most of the elements occur naturally, such as hydrogen, helium, sulfur, or some of the elements are there as a part of the periodic table, and we make them artificially, such as Einsteinium. It's actually a dedication to the famous scientist Einstein. Coming on to compounds, compounds are formed when two or more elements chemically combine. Now, this is actually a combination. The combination can be in between the same element. The combination can be in between different elements. If the combination is between the same element, we still call them elements, all right? We tend to call them compounds sometimes, but we're going to make that bifurcation really right after this paragraph, all right? So if we talk about hydrogen and fluorine as elements, they can combine to form hydrogen fluoride. This has a specific formula. We write it like this. For example, magnesium and fluorine may also combine. They can form magnesium fluoride. We formulate it like this. Elements combine in specific ratios. These ratios are actually the identity of that specific element. For example, the formula for carbon dioxide is CO2. All right. So CO2 is carbon dioxide. It can't be CO. It can't be C2O2. It can't be C2O3. Any change in these numbers and you change the entire identity of the substance. All right.
Mm.
This is the only one which is carbon dioxide. All right. This is something else. This is not carbon dioxide. Maybe you're familiar. This is carbon monoxide. This does not even exist. This is carbon suboxide. So we have different numbers. If we have different numbers, the identity is different, and that's an entirely different compound. For example, if I
So
talk about
like
water, water is actually, yeah, you were about to ask something?
yes, so actually in our test our teacher there was one question and it was like one formula and she said to say how many compounds, I mean elements are there.
Right, I am coming to it, but let's first answer your question. When we talk about these formulas, what's important is that every formula has, every element has actually a symbol. Let's say we
Yeah.
represent hydrogen with capital H. This actually is composed of a single letter. We represent, let's say, magnesium with Mg. This composes of two letters. What you would notice
Yes.
is that every time we show you a symbol of an element, the first letter is always capital. The subsequent letter, be it the second letter or the third letter, they are always small. So
Mm.
that's the way of writing it. When we talk about symbols, and this is something that is usually explained in class 6 or 7, is that symbols, the first letter is always capital, every subsequent letter is always small. If you make any changes to this, you're not writing symbols correctly, and they're not even considered for correct marks. For example, you cannot
No.
write this H like this. I'm coming to your question. Just let me go with the
Oh,
prerequisite first. I'll come to your question because
wait.
I'm going to give you a very easy tip how to calculate the number of elements in a compound. Now, you cannot write
Yeah.
it like this. You cannot write it like this. You cannot write it like this. You cannot write it like this. All these methods are wrong. Which
Mm.
brings me to your question. Now, if you are given a formula, let's say you have been given this formula, maybe your teacher gives you a formula like this one. The number of capital letters represent the number of different types of elements in the formula. That's why we are so specific about this one. Because if you make any changes, you actually change the whole identity. Take a look. This is a capital C and a capital O, which means it has two elements. Take a look at this formula, a capital N, a capital H, a capital C, a capital O. There are four different elements in this formula. All right.
Mm.
For example, like this, capital C, capital H, repetition of capital C, capital O again, and repetition of capital H. So actually capital H, capital C, and capital O, three elements in total, three different types of elements.
Yes.
All right. Let me tell you, this one and this one are two different things. Capital C, capital O, capital C, three elements. Capital C, but a
Mm.
small o and a capital C again, two elements. A
Yeah.
capital C represents carbon, a capital O represents oxygen, a capital C and a small l represents chlorine. But a capital C and a small o represents an entirely different element, that is cobalt. And then the Cl represents chlorine again. That's why I
Mm.
was giving you this example. So if any teacher comes up with any element, oh sorry, any formula of a compound, and there are billions, trillions, even more compounds on the planet, this is the easiest way to know how many different elements are used in there. For example,
Mm.
let's give you something complicated. Okay, let me think about it. Okay. Just don't, I am actually giving you something really complicated. Don't worry how big this formula is. Don't get scared from it. Just try using my
Yeah.
tip and telling me how many different types of elements are present in there.
Okay. I'll say.
Go ahead.
Okay. So first F is capital, so one. Then S,
All right.
so one, two. Then O.
Right.
Wait. Okay. So three, right?
3. So this is an
Okay. And
entire element, Fe. So separately, this is a separate element. This is a separate element. Go on.
yeah. And then A.
Right. Let's
And then
include the
S.
small one with it. Right.
Yes. Then SO again.
Right.
And then H and O again.
So there may be repetition. If you exclude all the repetitions, how many different types of elements are in there?
Um, 8.
Exclude the repetitions, please. Don't include them, since this is also the same element as this one, as this one. So why
Oh, okay,
include them
okay,
again
okay,
and
okay.
again? So exclude the
Um,
repetitions. And if you exclude all the repetitions, how many different elements do you end up with?
6.
Right. So this is first, this is second, this is third, this is fourth, and this is fifth. Where is
Oh,
the sixth?
okay. Oh, yeah, yeah, okay.
Okay, get the
I
point?
counted the last one. Yes, yes.
Okay, great, great. Okay, let's do something different. Um, let's try again.
Okay. So,
So
1, 2, 3, 4. 4. But if
first,
we like, okay,
second,
then wait.
third,
After
and fourth. Perfect,
fourth.
right?
Yes. Yeah.
So great. This is one element. This is the second one. Since we include the capital small letter with the capital letter, with the recent capital letter, this is the third one. This is the fourth one. Calcium, chlorine, hydrogen, oxygen. Since soon you'll get familiarized with these elements, so you would be able to name them too. Now, I
Mm.
guess you have found the answer to your question, right?
Yes.
Good, good. Let's continue. So what I was trying to say at that time was that you might have already know that the formula for water is H2O. That's because if you
Mm.
see at this structure, there is a big oxygen atom shown with a red color that is combined with two hydrogen atoms, which are pretty small as compared to oxygen. So those are shown with white color. And in every structure, you can see one oxygen and two hydrogen atoms, right? Now, this
Okay.
is the identity of water. You can't change these numbers. If you try coming up with some new numbers, let's say you try coming up with like this, or you try coming up with like this is not water.
Mm.
Let me tell you, this is another compound. The name of this compound is hydrogen peroxide. This can actually dye your hair, right? So hydrogen peroxide sometimes is a part of color hair colors, hair dyes, right? This is
Oh,
hydroxide. This, if present in a good amount, can actually burn your skin. So this is water which is necessary for life. So if you try changing these numbers, that's why we have been saying the elements always combine in fixed proportions, right? You change the entire identity. So make sure when you're writing the subscript numbers, these numbers, make sure you do them with care and make sure you do not intentionally change them on your own. Okay, good. Some compounds are water. We are familiar with water. We use it every day. Then there is silicon dioxide. Silicon dioxide is a big part of sand, right? And sodium chloride. Sodium chloride is NaCl. It is the common table salt. It is the same white salt that we eat every day, right? And they have tried to show you diagrams to tell you that the structures can be entirely different from one another. And you might notice that the way they have been drawn, all three of them are very different to one another. We'll continue discussing their structures in the bonding chapters. Ionic bonding, covalent bonding is all about this, how they are bonded, and why the structures look like so. So I'm going to clear it up and let's move forward to our very next definition, mixtures. In a mixture, as the name suggests, various substances are mixed together. There are no chemical reactions, they're simply mixed. For example, a nitrogen gas, a nitrogen molecule is composed up of two nitrogen atoms, which are shown over here with two blue balls. An oxygen atom, on the other hand, are shown with two red balls, right? So it's just a mixture. There are some blues, there are some reds in this diagram, and they're not reacting with one another. Now, mixture can be made with elements. Mixture can be made with compounds. You can see water over here, or here, or here, right? Or you may see carbon dioxide. This is for carbon dioxide, CO2. This is for water, which is H2O. So that's a mixture of compounds, right? Or you can even mix an element with a compound. You can mix nitrogen with carbon dioxide. So mixtures can be made from either elements. You can mix two elements like this one. You can mix two compounds like this one. You can mix an element or a compound like this one. And they can be in any proportion. Mixtures can be in any proportion, the proportion we want them to. For example, if I talk about your daily life, I would take a salad or a fruit salad or a vegetable salad as a good example of a mixture. Let's assume that your mom asks you to make a fruit salad. Now, what I've seen with children doing is that when it comes to fruit salad, what they tend to do is that they tend to fill it up with the fruits that they like, and they try to fill it in with least amount of the fruits that they dislike. Or if possible, they don't even throw in a single piece of a fruit that they dislike, because later at when they're about to eat it, they are again going to put that specific piece of the fruit that they dislike away from the whole salad. They're not going to eat it. They're going to put it at the side of their plate or bowl, whatever that is, right? So the proportion can be changed. Let's say you have bananas and apples and grapes and mangoes, and you love apples, so you're going to add a lot of apples in your salad, right? So you change the proportion. Let's say another sibling who likes mangoes more is going to put a lot of mangoes in there. So again, a different proportion. So mixtures can be made with different proportions. For example, any amount of sugar can be taken into a cup of tea or coffee. I've seen people taking less sugar, half a tablespoon or 1 tablespoon. I've seen people who love sugar throwing in 3 tablespoons into a cup of tea, which is really too much, until it becomes saturated.
I
Right?
used to only. Yeah.
Okay, good, good. But too much sugar is not good, so it's better to learn that thing from an early age. Now, doctors and people everywhere are trying to create the awareness of diabetes, that it is due to the sugar. So it's better to have it as a balance. All right. So
Okay.
coming back to it, simple differences between mixtures and compounds. How are you going to differentiate it? Now, before I move on to this specific point, I want you
Mm-hmm.
to uh, ponder on this diagram and notice the differences between the mixtures and compounds or elements. Now, one thing you can easily note with every element, you'll find the same colors in the same size of balls, right? When it comes to compounds, you would always notice different colors combined together,
Mm.
right? And when it's a
Yes.
mixture, you'd instantly come to see that two different things have been mixed together, be it an element or a compound, be it a compound or a compound, be it two different elements, you'd easily be able to see a mixture, or you'd easily be able to spot a mixture as soon as you see a diagram. And I've
Okay.
seen
Yes.
these diagrams being used by examiners, though that's an easy task to do, but sometimes they use these diagrams as a part of an MCQ or as a part of a question, and spotting the differences should be something easier for a student. I hope you also find it easier, right?
Yes, it's easy.
Good, good. If you find it easy, let's move on. Let's actually move on with the simple differences. Now, the first difference
Yes.
that we can talk about is proportions. In water, which is a compound, every single water molecule has two oxygen atoms, and there is one oxygen atom that they are combined with, and it never varies. I've already explained this part. Now, in a mixture of hydrogen and oxygen gases, it is going to be different than water. Now, what he's trying to make as a point is that if this is the structure of water, let's say
Mm-hmm.
like this, I'm trying to copy this structure, and this
Mm-hmm.
is the structure of an oxygen molecule. This is a structure of a hydrogen molecule. I think you can easily differentiate between these. If
Yes.
this represents oxygen, if this represents hydrogen, you can easily understand this is H2O, this is O2, and this is H2, right? Since
Yes.
the numbers only represent the number of atoms have been combined in the diagram. So you can easily spot a mixture of hydrogen and oxygen, or a molecule of water in between, right?
Yes.
If you had some iron metal and some sulfur, you could mix them in any proportion you want to. But in case of iron sulfide, a compound, the proportion would always remain the same, one molecule of iron as compared to one molecule of sulfur. They're always going to
Mm-hmm.
remain the same, since that's a compound. In case of mixture, the
Okay.
proportion can be different. In case of compound, it has to stay the same, right? I
Yes.
hope you get the point. Okay. So the
Yes.
difference of proportion always comes in mixtures, but never in elements or compounds. Now, the next thing that can be different are properties. In a mixture of elements, every element keeps its own properties, but the compounds are quite different. Now, I'm going to use the same diagram. Okay, I'm going to erase the rest of the parts. And I'm also going to move a little bit below so that you can see. Now, what he was trying to say is that in case of elements like this one or this one, they tend to keep their properties. Let me discuss a property as an example. Hydrogen is a flammable gas. It catches fire easily, and it actually really explodes too quickly with a big, loud sound. Oxygen, on the other hand, is actually a gas that helps with combustion, that helps with burning. Without oxygen, we cannot burn something. Actually, oxygen
Mm-hmm.
is the reason why everything burns. If you're burning a piece of paper, it requires oxygen to burn. If you remove oxygen from that system or surroundings, it would stop burning immediately. All right. And
Mm-hmm.
this burns with an explosion. This helps with the burning. But when these two combine, this is something which actually extinguishes the fire. Notice uh, how fascinating the facts are. This burns with a loud explosion. This helps in the burning. If this is present, only then hydrogen is capable of burning. But when these two combine together to form a compound, the compound has an entirely different set of properties. That compound can be used to extinguish the burning flame. What is commonly
Mm.
used to extinguish the fires out, right? So
Yes.
if there is a mixture consisting these two, this mixture will keep the properties of hydrogen and oxygen. Okay, so the elements
Mm.
tend to keep their properties in a mixture. The compounds are
Actually,
different.
I did not understand this property.
What I'm trying to say is that when the elements are combined or the compound is combined in a mixture, they tend to keep their properties. For example, you take a container and you fill it with some hydrogen molecules, and at the same time, you fill it with some oxygen molecules, and then you bring
Yeah.
a burning matchstick in, they will burn. Since we have the gas that can burn and we have the gas that helps hydrogen to burn. But if I react them together and I completely convert all of these molecules into water molecules, right? And I only
Mm.
have water in the system and I bring a burning matchstick into it, it will quickly extinguish, which gives you the idea what? That as long as the elements were there, they kept their properties. But when they were converted into a compound, their properties changed into a new set of properties. And then the properties of compound was shown, not the individual elements. All right.
Yeah. Okay. Yeah.
Okay. Let me define it in a different way, since you might be having a hard time with it. So let me define it in a different way. Now, what I'm trying to define is that the components that form something, some product, actually may be able to lose their properties at all. For example, any component like, let's say, we have components for the tea, right? So if you add some
Mm.
milk, if you add some powder, if you add some sugar, you make something entirely different from any individual component.
Yes.
The tea was just black powder. The sugar
Mm.
was just small white cubes, right?
Mm.
And the milk
Yes.
was a white liquid. The product is actually different from all three of them, has its own set of properties, has its own appearance, has its own color, has its own properties, which is different from the individual elements, right?
Yes.
Make sense? So what I'm trying to say is that when the elements combine, they lose their properties and the compound gets a new set of properties. So if the
Mm.
mixture contains the elements, the properties of elements would be shown. If the mixture consists of the compound, the properties of the compound would be shown. Whatever the mixture is composed of, those specific set of properties would be shown. All right,
Mm. Mm.
get the point?
Yeah. Sort of.
Okay, let's take another kind of mixture. How many siblings are you? I'm going to make it a little bit of fun.
Uh. 5.
Okay, I'm going to assume something. Let's say we have you as the first sibling A, and then there is another younger sibling B, and then another younger sibling C. You are the one who is mature, right? Who understands what's what
Mm.
and stays in the at the time. Then the other one is actually pretty naughty. And the last one
Mm.
is rude. I shouldn't be using this word, but I'm trying to mix different combinations. So
Yeah. Yeah.
if
No.
in a room, I only allow two siblings at a time, so I would only be able to see two different sets of properties at a time, right? If I only allow A and B in a room and I try to interact with them, I would find one mature and one naughty person in the room. If I
Mm.
don't allow B in the room and instead I allow C in the room, I'll find one mature and one rude person in the room if I interact with them. Make sense? So in the
Yes.
same similar way, if I allow hydrogen or if I allow oxygen, they are going to show their set of properties. Make sense?
Yes. Yes.
Okay. I guess now it's a little bit more clear than what it was
Yes.
previously. Okay.
Yes.
And at the end of it, I would like to say exclusively, I'm not calling any of your siblings or you as naughty or rude. It was just an example. All right. I
Yeah.
hope
Yeah.
you get that.
No problem.
Okay, good,
Okay.
good. Once I was about to trying to explain to my student an assumption, and he
Mm.
actually got angry. He thought I was calling him or his siblings as rude and naughty. He agreed that his siblings are rude and naughty, but he never agreed to the fact that he can never be rude or naughty. And I told him it was just an assumption, it was just an example. Nothing actually exists in reality. All right. So moving on. For example, in a mixture of iron and sulfur, iron is gray, sulfur is yellow, but when they react with one another or they react with some other things, for example, iron reacts with acids and they produce gases. Sulfur does not react with acid. However, when we form a compound out of them, which is iron sulfide, which is actually a combination of both iron and sulfur, it really is quite different from its elements. And with acid, it produces poisonous gases, which smells of bad eggs, right? So the
Mm.
compound that we are forming out of the elements can be entirely different from the elements themselves in the matter
Mm.
of appearance, in the matter of colors, in the matter of odors or smell, in the matter of how they behave or how they react. A mixture of hydrogen and oxygen are colorless gases. They explode when you put a flame to it. The compound water is actually a colorless liquid. It's not even a gas. And it actually puts out a flame, distinguishes it. So the
Mm.
compound can be really different from the elements from which it is made, right?
Yes.
Okay. We even usually come up with the examples. Biology teacher come up with the examples of showing the faces that a child face is different from their parents. Although they have resemblance to their parents, but a child's face is different from their parents. The mother has a
Mm.
different face, the father has a different face. The child may have the resemblance to one of them or to both of them or
Sort of
to,
like mixture.
right?
Mm.
So I hope you get the point.
Yes.
Good, good. Now, the next thing we need to discuss is ease of separation. Now, this is going to be different from with compounds as compared to mixtures. I'm going to start with the easier one first. Mixtures are easy, right? Let's take the example of the same salad. Let's say your salad has apples, bananas, some grapes are in there too, and some mangoes. Let's assume it has been made by one of your siblings, and trying to be
Mm.
naughty, she put in something that you don't like. Let's assume you don't like grapes.
Yeah.
Now, when you're about to eat it, what are you going to do for separation? Whenever
I'm
a
just going to
grape
take it.
comes, yeah, you're gonna take it out by
Yeah.
simple hand picking or by simply just putting them away with the help of the spoon or even your
Yeah.
fingers. You're not gonna eat the grapes, you're gonna eat the rest of it. So if I
Yeah.
say the mixtures can be separated by easy physical means, I hope you understand we can do it easily. In case of
Mm.
salads, it was easy to handpick, but sometimes we can do it by changing the temperature, dissolving a part of a mixture in a solvent, or such as mixing it in water, or with some methods that do not involve chemical reactions, some basic, easier methods, right? For example, if
Mm.
you have a mixture of iron and sulfur, now you know iron is a metal, you know it can be getting attracted to a magnet. You can take a magnet,
Mm.
put it on the top of this mixture, all the iron would stick to the magnet, the sulfur will not. So it was
Mm.
pretty easy to separate it by physical means. You never went on with
Mm.
any of complicated chemical reactions. You just brought a magnet and you just separated the iron. That's about it, right? But
Mm.
if that iron and sulfur was changed into iron sulfide, no matter how many times you bring a magnet closer, you can't take the iron out of it,
Mm.
right? For example, if you
Yeah.
use some milk, and if you use some tea powder, if you use some sugar, right? You can't take them
Mm.
and you convert it into a tea. Let's say this is tea powder, convert it into a tea. Now, if you want to take milk out of the tea, you won't be able to do that easily. Can you?
Yeah. No.
Right? So you do understand in case of compounds, the ease of separation is not easy. It requires a chemical reaction.
Mm.
But in case of mixtures, it can be as easy step as hand picking or separating them with the help of a magnet or with dissolving something or with changing the temperature, stuff like that, right?
Yes.
So
Mm.
physical processes are the processes. These can be separated by simple physical processes. Physical processes are
Yeah.
the processes in which we change the temperature, we may be melting them, we may be boiling them, and these are usually separated by chemical means. We need to go with the chemical reaction to separate them. And chemical reactions are different to carry out as compared to the physical processes. For example, if you
Mm.
have a mixture of oxygen and hydrogen gas, what we do is that we condense oxygen and we convert it into a liquid. As compared to hydrogen, that's something easier to do. At the same temperature, nothing would happen to hydrogen, but the oxygen would be condensed into a liquid, right? So you
Mm.
can separate the liquid oxygen. Since hydrogen would be present in the form of gas, that's very easy to separate, right?
Can you explain? Like, can you explain this again?
Yeah, it's pretty easy to explain if you draw a diagram. Let me draw one for you. Now, what we are going to do is that we're going to have a mixture of hydrogen and oxygen. So I'm going to draw a little bit of diagrams for you. You'd know what I'm talking about. Now, you can see a few molecules of oxygen in there, and you can see a few molecules of hydrogen in there. What we're going to do is that
Yes.
we are going to lower the temperature. Now, he already told you that oxygen condenses into a liquid at negative 183 degrees centigrade. If we want to convert this oxygen into a liquid, we need to drop the
Mm.
temperature down to this one. If we want to convert hydrogen into a liquid, we need to drop the temperature down to this one. But negative
Mm.
183 is easier to approach because this is much more cooler temperature, negative 253. So once we start lowering down the temperature and we get to negative 183 degrees centigrade, hydrogen becomes liquid. In that, and in that case, in the form of drops, it is collected at the bottom. It won't then stay in the center of this container. Since it's a liquid, it will actually settle down, level down. And what would
Mm.
we be left with? There would be no oxygen in here. It would be just hydrogen on top and oxygen at bottom in the form of a liquid. Can you separate a liquid
Yes.
out of a container? You easily can. Tilt the container,
Yes.
you'll easily be able to slide the liquid out of it, right?
Mm.
And there you go. You have
Yes.
separated hydrogen and oxygen. The gases which seem very difficult to separate, you have easily separated them. But once you convert this hydrogen and this oxygen into water, no matter which temperature you lower it to, or no matter which high temperature you go to, you cannot separate these two hydrogen atoms from this oxygen atom. No matter you get to 100 degrees centigrade, no matter you get to 1,000 degrees centigrade, no matter you get to negative 200 degrees centigrade, you would only be able to boil water, freeze water at these temperatures. You won't be able to separate hydrogen and oxygen atoms from one another, right? You do understand if I'm
Yes.
going to go to 100 degrees centigrade, I'm going to boil this water and the water will be converted into steam. You already know if I go down to temperature of negative 200, even negative 200 is a far away thing. If I get down to just 0 degrees centigrade, I'll freeze the water into ice, but I won't be able to
Mm.
separate hydrogen and oxygen atoms, right? There is a separate
Yes.
process in chapter number 10 by the name of electrolysis, in which we chemically differentiate and then take these hydrogen atoms out of this oxygen. We break the structure of water, and we do that by a chemical
Okay.
reaction. You can't do that in a physical process. Physical process is just a separation technique, just like the same thing you
Mm.
did with the salad, right? We
Yeah.
did the same thing with the
Mm.
hydrogen and oxygen over here. I think now it makes much more sense, right?
Yep.
Good, good. So now you know a few things about compounds and mixtures. First thing, you know that the proportions can be different for a mixture, but it remains the same for a compound. You can't change it for a compound. The second thing you know is that in mixture, elements keep their properties, right? In
Mm-hmm.
compounds, elements do not keep their properties. The properties of compound is much different from the elements it is made from. Lastly, for the ease of separation, you know, mixtures can be easily separated by simple physical processes, simple physical techniques, separation techniques, hand picking, tilting the container, increasing or decreasing the temperature, separation like that. But in case of a
Yeah.
compound, we need to go with complicated chemical reactions in order to separate them. So these are the three things that we need to understand about the basic differences between mixtures and compounds. I hope you get all three at the same time when I summarize it like this. Do you?
Yes.
Good, good. Then I guess it's easy to move on. So the next thing is melting point and boiling point. Now, since I was discussing previously that we can either increase the temperature or decrease the temperature, you should be able
Mm.
to understand the melting points of elements, compounds, and mixtures. Since we're studying all three of them, so let's talk about the melting points and boiling points for all three of them. What I'm going to do is that instead of going with all of these paragraphs, I'm going to go with
Mm.
some a small table to help you with it. So sharp, 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 and over a range, and over a range. Now I've used the same words for elements, compounds, but I've used entirely different set of words for mixtures. Now, what does the word sharp means? First thing, when I use the word sharp for elements or compounds, I hope you remember that we discussed about water, that the melting point of ice was 0 degrees centigrade. Now that's a sharp
Mm.
number. You know that exactly at 0 degrees centigrade, the ice would melt into water. Or
Mm.
in case of boiling point, you know exactly at 100 degrees centigrade, the water will boil and will convert into steam. This is the case for compounds and elements when you can describe them at a single temperature point, at a single number, we call it with the word sharp. That's what the word sharp means. When I use the phrase over a range, for example, I don't talk about water anymore. I talk about mineral water. Now, mineral water, in case of mineral water, the melting point is usually less than 0.
Mm.
It can be -1, it can be -2, it can be minus 0.5, it can be anything less than 0. In case of boiling point, you will be astonished to know for mineral water, it may boil at 100.1, it may boil at 101, it may boil at 102, it may boil at any temperature. That's why we use the phrase over a range, anywhere from 100 to 102, anywhere from 100 to 105. It's not as
Yes.
exact as the compound was or as the elements were. Mixtures have a problem that they melt and boil over a range of temperatures. And the same thing would be stated over here. Pure substances such as elements and pure compounds, they melt and they boil at fixed temperature. Use the word fixed instead of sharp, which is a much better term and easier to understand term. For example, melting point of water is 0 and boiling point is 100, and they are going to exactly melt and boil at the set temperatures. Mixtures, usually melt or boil over a range of temperatures, as I've shown you in examples over here. The presence of
Yes.
impurity, actually, what happens with the presence of impurity, and now we need to understand how the melting or boiling point changes. The presence of impurity lowers the melting point. It won't remain the same, and it won't go higher either. It would always be lower, and it raises the boiling point. Now, you might notice that for mineral water, the melting point never increased from 100, it decreased from 0. No, sorry, not 100, 0, right? And boiling point, instead of getting decreased from 100, it actually increased from 100. So I said
Mm.
the same examples because I knew that the melting point is lowered, it decreases, and the boiling point is raised as soon as you introduce an impurity in water. Which means if you have pure water and you just boil it at 100 degrees centigrade, take a pinch of edible salt, the white salt we eat every day. A pinch is a very small amount. I hope you understand. Pinch only includes a few particles in between your two fingers. I hope you understand what a
Yes.
pinch is, right? And add that pinch of salt to that water you just tested that boils over 100 degrees centigrade. After adding that pinch, try boiling it again. It won't boil at 100. It would boil at any temperature above 100, but not 100. Why? The presence of impurity increased or raised at boiling point. For example, just dissolving 10 grams of cobalt table salt in 1 liter of water lowers the melting point about this many degrees centigrade and raises the boiling point about this many degrees centigrade, from 100 to 100.2 and from 0 to negative 0.6 degrees centigrade. Although the changes are minor, but there are changes. And I hope you understand
Yep.
the changes now. The changes in case of
Yes.
melting point would be less than the original temperature. That's why I use this less than sign, and it would be greater than 100 degrees centigrade. So you can easily use the greater than sign. Make sense?
Yes.
Now, this would also give you an idea. Let's say they came up with an example. Let's say in exams, they go with a question that goes with something that you never really know about. They come up with the name of a
Mm.
compound and they tell you, sorry, let me come up with some different compound. This might not help in this case. Let's say they come up with a compound. They say this is the name of the compound. This is the formula of the compound. They try to confuse you with extra pieces of information. And they tell you that this actually boils, the boiling point is exactly at 78 degrees centigrade. They took the compound, they tried to boil it, and they boil at the same set temperature. What does that tell you about the compound? That the substance is pure. If the boiling point is 78, and when you tried to boil it, it boiled at 78 again, this proves the
Mm.
compound was pure. Because if it wasn't pure, if there was an impurity, it won't be the compound. It would actually become a mixture, because a mixture is not a pure substance. Even a small amount of unbonded substance may be known as impurity, and impure substances actually are all mixtures. That's what impurity is, a mix.
Mm. Yes.
Good. So they can come up with
Yes.
any compound in paper. They can tell you its boiling point, and they can give you a scenario. If it boils at the same temperature, it means it's pure. If it doesn't, let's say it boiled at 78.3 degrees centigrade, what does that tell you? It's impure. It's probably a mixture. Some impurity has been mixed into it. Make sense?
Yes.
Sometimes they don't give you an exact point. Sometimes they tell you that it uh, went over 78 degrees centigrade. Going over 78 degrees centigrade also gives you the same idea. It's impure. Because anything
Mm.
above 78 in case of boiling point gives you the idea that there was some impurity involved. It was a mixture. It wasn't a pure compound. Make sense?
Yes.
And they have taken the example of aspirin, which is a common tablet for headaches around the world. It's a white powder. It melts at a specific temperature. Now, if the sample that was given to you melted at this range, this would quickly give you the idea that the tablet you got was impure, right? So why
Yes.
is melting and boiling point so important? And let me, from this example of aspirin, I think you get an idea. The purity is very important. When we talk about purity, it is very important in three aspects of life. Number one, food. If your food is not pure, if it consists of something that is unwanted, even your mouth is automatically going to reject it. How? It is either going to smell it, or it is either going to feel it by touch, or it is going to feel it with in terms of taste. For example, if you don't
Mm.
know about something that has been deteriorated and you put it in your mouth, as soon as it tastes bad, you're going to spit it out. If you don't know
Mm.
something has already turned bad, you bring it closer to your mouth to eat it, and at the same minute your nose smells something different. You're not going to put it in your mouth. You're straight away going to stretch your hand away from your mouth. No, this is something bad.
Mm.
This doesn't
Yes.
smell good. Your mouth rejects it. You reject it as a person, right? Let's say
Yes.
you get a sandwich, you put it in your mouth, it didn't smell bad, it wasn't bad in terms of the taste, and then there was a small piece of stone in there which actually scratched in between your teeth. You're immediately going to spit it out. You are going
Yes.
to actually uh, put that away, spit it out. Your mouth is going to reject that food. Same happens with drinking water, the second aspect of life where purity is extremely important, right? And the third one
Mm.
is medicine, where purity is important. Any impurity might not be helping you with the medicine. So there are three aspects of life where purity is important, and melting the substance or boiling the substance gives us the idea whether it is pure or not. Since aspirin melts at this temperature, you get a full batch of these tablets and you want to check them, you can simply melt them. If they melt at any temperature lower than this one, you would immediately
Mm.
know that somebody is trying to scam you with a bad set of tablets, right? Easy. So
Mm.
chemistry is actually being
Yes.
helpful in daily life. So that's why melting and boiling points are important. I hope you get the idea, right?
Yes.
Great, great. Moving on, just let me check. There are a few separation techniques that we need to discuss before the chapter ends. One half of the chapter is done. We'll do the second half in the second sitting since it's about time.